Hello there. So we're going to talk about theorems of zeros about polynomial functions. Continuing our talks on polynomial functions. So we have two theorems that are important and they're very similar here. We have our non-real zeros theorem as well as our irrational zeros theorem. And what they say is that any non-real, any complex or imaginary zeros are always going to occur as a conjugate pair. So that means if one of them has a plus, one of them has a minus. And that's the same for our irrational zeros theorem. Those will also occur in conjugate pairs. And irrational numbers are things like the square root of 2, or 5 plus the square root of 2, or 2 minus 8 square root of 3. Those are all irrational numbers. So what we just want to remember is that imaginary numbers, square root numbers, whenever you have those as solutions, you have to have the conjugate pair. One thing you can think about is the fact that we know our quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. And what we know is that imaginary number or irrational number is determined by what we have under the radical, which we call the discriminant. And if the discriminant is negative, we get an imaginary number. So we would have plus or minus that imaginary number. And if the irrational, or if the discriminant, that radicand under the radical, we call that the discriminant, if that is something that you can't easily take the square root of, like 5, that would remain to give us an exact answer. And again, that would be plus or minus the square root of 5. Okay? So the factor theorem is review. We know that. So if you know, all this says is if you know a 0, then you can write the factor. And then as we move further into this section, we talk about the rational zeros theorem, the rational root theorem. And that's going to help us also when we're factoring polynomials. And essentially what the rational root theorem or the rational zeros theorem does is it says, hey, we can factor anything. We've learned about using the synthetic division to factor things in our examples from the last section. So if we didn't have a starting point and I said, hey, factor this, you would just test random numbers with synthetic division. However, testing random numbers could be rather tedious because how many numbers exist? There are infinite numbers. So what the rational zeros theorem does for us is it narrows it down to a list of possible zeros. So instead of having infinite numbers to choose from, maybe we have 20. Right? And you're going, oh, Miss Stein, 20, that's a lot of numbers. Well, compared to infinite, it's really a microscopic quantity. And so we can determine a list of possible zeros by listing all of the factors over our constant, or of our constant, over all of the factors of the leading coefficient. And then that creates a set. And then we're going to use the positive and negative values for that entire set. All right, so now that we understand our theorems, let's do an example. And this first example is pretty simple here. We're going to write a possible equation of a third degree polynomial with -2, 0, and 5 as zeros. And so what we know from the factor theorem, the factor theorem says, up above and from a previous section, is if the 0 is c, then x minus c is a factor. So if I have 3 zeros, I can write 3 factors. So I've got f of x equals x minus, my first 0 I have listed here is -2. So x minus -2 And then I would say x minus my next 0 is 0, x minus 0, and x minus the last 0 I have listed is 5. Okay, so using my factor theorem, I'm able to write this out, and this represents a possible polynomial function that would have these zeros. I can simplify this. That becomes x plus 2 times x minus 5. And continuing to FOIL, I could end up with x squared plus 2x times x minus 5. And I have x cubed plus 2x squared minus 5x squared. So that would be minus 3x squared minus 10x. So here I have a cubic polynomial that has -2, 0, and 5 as its zeros. It's not the only polynomial, but it's a possible one. Okay? And there are multiple correct answers here, so we just try to make the least amount of work and include the least amount of numbers so that this works out. You may see some problems that ask you to leave your answer in factored form. And you may have some where you need to multiply it all the way out. Okay? So we're going to do a very similar problem here, but we're going to employ the other two theorems we talked about at the beginning of this video. We're going to use our irrational zeros theorem and also our complex zeros theorem. Okay, so we're going to write a possible equation of a least degree polynomial, keeping our values as small, adding the least amount of numbers as possible, with -1, 3 plus I, which is complex, and square root of 5, which is irrational, as zeros. So, one thing we know is that complex and irrational zeros must occur as conjugate pairs. So the zeros that we are given, well, we're given x equals -1. We're given x equals 3 plus I. And 3 plus I is complex. So that means I also have x equals 3 minus I. Okay, so complex numbers occur in conjugate pairs as well as irrational numbers. So since I have positive square root of 5, I also have x equals negative square root of 5. So I have 5 zeros. Even though this looked like I would only have 3 zeros, and this would be cubic because one of my zeros was complex and the other zero I had here, square root of 5, was irrational, I had to write those as conjugate pairs, and that means the sign in front of the square root or the sign in front of the I has to change. That's what a conjugate is. So we have 5 zeros. That means we're going to have a 5th degree polynomial. And if I write this out using my factor theorem, so if I know a zero, I know a factor is going to be x minus that value. So x minus -1, x minus -1 is actually x plus 1. I'll have a factor x minus the quantity 3 plus I, as well as a factor x minus the quantity 3 minus I. I have x minus the square root of 5 and x minus negative square root of 5. So I have 5 factors that I need to multiply. And before I do that, I'm going to make sure I'm going to simplify out some of these double negatives or distribute. So I have x plus 1, x minus 3 minus I, and x minus 3 plus I. x minus the square root of 5, and x plus the square root of 5. So as we look at simplifying this, it's very important that we multiply our conjugate pairs first, okay? Because that's going to get rid of the i's and get rid of the square roots. So always make sure you multiply your conjugate pairs first. Doing this, and a tool that can help us, would be to use the area or the box method. So I have 3 terms by 3 terms. I have x minus 3 minus I times x minus 3 plus I. And you can FOIL the regular way. I have just found over years of teaching, this is an area where students make mistakes, and if you lose one sign, the whole thing's off. We're doing a lot of multiplication here, so we're going to use this graphic organizer, our box method, area method, to help us keep things straight. So x times x is x squared. Negative 3 times x is negative 3x. X times negative I is negative xi. And then I get negative 3x, positive 9, positive 3i, positive xi, negative 3i, and negative I squared. And we want to make sure what we know about I squared. Remember, I squared equals negative 1. So negative I squared is negative 1. We should get a positive 1 for that value there. Okay, I squared equals negative 1. So I'm going to go ahead while I have my screen like this and multiply these other two. X minus 5, or x minus the square root of 5, and x plus the square root of 5. So minus root 5 plus positive root 5. That gives me x squared minus the root of 5, x plus the root of 5x, and minus the square root of 5 squared. Okay, and squaring a square root, what that gives me in here is just negative 5. Okay, so writing this out, I have p of x equals x plus 1. So what I've written in red, this is all going to multiply together. And negative 3x and negative 3x, that's going to give me a negative 6x. So I have x squared minus 6x. What you should notice about my I values, negative xi, positive xi go away. 3i and negative 3i go away. And then I'm left with 9 and negative I squared. That's 9 plus 1. So we end up with a plus 10. And then we have x squared. Dealing with my root 5x, those are opposite terms. They cancel, so I end up with just x squared minus 5. All right, so at this point, it's just busy work multiplication. Take a moment, pause the video, practice your multiplication. I'm going to pause it and write my answer out. And so doing two operations of multiplication. This first operation here gives me x cubed minus 5x squared plus 4x plus 10. And then we still have to deal with multiplying x squared minus 5 through. So the final answer is the possible polynomial function of least degree is x to the 5th minus 5x to the 4th minus x cubed plus 35x squared minus 20x minus 50. And of course, we expect to get x to the 5th as our highest power, our degree here, because we started with 5 zeros. So one more example in this video, and we're not going to do all of the multiplication, but we're going to incorporate multiplicity in. And remember, multiplicity is the exponent on each factor. So we're still using our factor theorem, but we're going to incorporate some multiplicity. So write the equation of the least degree polynomial with 0 as a 0 of multiplicity 5, -2 as a 0 of multiplicity 6, and 7 as a 0 of multiplicity 3. So my possible function f of x equals, I have x minus 0, x minus 0, and the multiplicity on this factor is 5. X minus, my next 0 that I'm dealing with here is -2, so x minus -2, which has a multiplicity of 6. And my last piece, we have a 0 of 7. So that would be x minus 7, and the multiplicity, the exponent on that factor, is 3. So I'm just going to tidy this up a little bit. This is the same as writing f of x equals x to the 5th. I actually don't need parentheses there, so I'll just say x to the 5th. X minus -2 is x plus 2 to the 6th, and x minus 7 cubed. So we are going to leave this in factored form, as it says in the instructions, but we could multiply that out if we wanted. And if we did, we would get something, we would end up with x to the 14th. Nobody wants to do that though, right? So we'll leave this one in factored form. But hopefully we have a better understanding of using the factor theorem and our theorems about irrational and complex zeros, and then incorporating multiplicity.